into the world of chemistry. We've got some awesome source material for this one, excerpts from a textbook called, get this, Basic Concepts of Chemistry. A concise overview, along with a really helpful briefing document that summarizes the key points. Perfect for us.
Perfect.
We're going to explore those core concepts, but also, get this, we'll uncover some surprising historical facts. You might even find yourself looking at the world a little differently afterwards.
It's always fascinating to see how chemistry is woven into our everyday lives.
Right. That's what I love about these deep dives. You never know what those aha moments are going to be. So, ready to unlock some chemical secrets.
Absolutely. Let's dive right in. Let's actually kick things off by taking a trip back in time. We're going to explore the roots of chemistry in ancient India.
Okay, ancient India, I know they were way ahead of the game in math and astronomy, but chemistry, I'm all ears, fill me in.
Yeah, it's more than just alchemy. Ancient Indian chemists, they were masters of practical applications. Think about it. They were using their knowledge to create things, to build, to heal. Take the Indus Valley civilization, for example. They were building with baked bricks and pottery way back in, like 3000 to 1500 BCE, in places like Mohenjo-Daro and Harappa.
Wow, that's a pretty sophisticated use of chemical processes for that time period. That's amazing.
It is. And even earlier than that, they were producing glass objects in places like Maski, Hastinapur, and Taxila. It's pretty incredible. Their techniques were surprisingly advanced.
It sounds like they were already working with a diverse range of materials. Did they, document their knowledge? Did they write things down?
They did. Ancient Indian texts, they're like a gold mine of chemical knowledge. I mean, the Sushruta Samhita, it actually mentions alkalis. The Taraka Samhita, it goes into detail about how to prepare acids. And the Resa Upanishad even describes gunpowder.
Gunpowder, seriously. That seems so far ahead of its time.
It is. And it just shows you the ingenuity and innovation that was present in early Indian chemistry. They weren't messing around. They were putting their knowledge to work. These weren't just like abstract ideas floating around.
So it wasn't just trial and error. It sounds like they had a real system in place.
Yeah.
Were there any individuals who really stand out, like any big names?
Oh, absolutely. Well, there's Nagarjuna, a total rock star. He was a renowned chemist, alchemist, and metallurgist.
Ooh, alchemist. That's a cool title. Okay, I'm picturing someone in a lab with bubbling concoctions everywhere. What did he focus on?
Well, his work, the Rasratnakar, it delved into mercury compounds and metal extraction. Really advanced stuff. And there's another fascinating text, the Zarnavam, from around 800 CE, that describes a really cool technique. You could actually identify a metal just by the color of its flame.
Wait, what? They could identify a metal just by looking at the color of the flame? That's like something out of a magic show. How does that even work?
Right. It's a pretty neat technique. It turns out different elements emit specific wavelengths of light when they're heated. So you get these unique flame colors. Really shows you their powers of observation.
So they were really laying the foundation for modern chemistry. Were there other key figures that we should know about?
Definitely. There's Chakrapani, for example. He's credited with discovering mercury sulfide. That's a bright red pigment, still used in art today, by the way. And get this, he's also believed to have invented soap.
Soap!
Yeah, using mustard oil and alkalis.
Oh, okay. Now that's an invention that really changed everyday life. I mean, it makes you think, right? Like, what other innovations from that era are we just kind of taking for granted?
It's true, right?
Yeah.
It's a good reminder that scientific knowledge builds upon itself over time, and so much of it has roots in these really diverse cultures.
Speaking of building upon knowledge, get ready for this. This one's a bit of a perspective shift, I think. The concept of atoms, which we often associate with John Dalton in the 19th century, right?
Yeah.
It actually existed in India, centuries earlier. No way. Are you serious? Someone in ancient India was already thinking about atoms. Who was this visionary?
His name was Acharya Canada, and way back in 600 BCE, he proposed the idea of these tiny, indivisible particles that he called paramanu, essentially atoms, and he described them as eternal, indestructible, spherical, and constantly in motion.
Wow. That's incredibly similar to our modern understanding of atoms. That's incredible. Really challenges the traditional narrative of scientific discovery.
Exactly, and it's a great example of how scientific thought can emerge independently, in different cultures and time periods.
Okay, my mind is blown. I need a second to process all of this. Maybe we should shift gears a little bit, talk about something a bit more familiar, like the states of matter.
Sure. It's always good to go back to basics.
Right. We all learned about solids, liquids, and gases in school. I'm sure there's more to the story than I remember.
Oh, there definitely is. It all comes down to the arrangement and movement of particles. You can picture solids as this tightly packed group. Everyone's in their assigned spot. And so you have this fixed shape and volume. Liquids, they're a bit more loose. The particles can kind of move around more freely, but they're still close together. So they have a definite volume, but they take the shape of their container.
Okay, so it's like a dance floor, right? In a solid, everyone's frozen in place, but in a liquid, they can move around, but they're still bumping into each other. What about gases?
Gases, oh, they're the wild ones, the ultimate free spirits. The particles are far apart, zooming around at high speeds, filling up any space they're in. So no fixed shape or volume for those guys.
I love those analogies. Makes these concepts much more visual. I feel like there should be, like, more, though. Aren't there other states of matter beyond those three?
You're right, it's not just those three. Plasma, for example, is often considered the fourth state of matter. Superheated, ionized gas, actually the most common state of matter in the universe. Think stars, lightning.
Wow, I never even thought of plasma as a state of matter. Anything else?
There's also something called a Bose-Einstein condensate. It's a state of matter that exists at extremely low temperatures. In this state, the particles start behaving as one single entity, like a superatom almost.
Okay, now that one just bends my brain a little bit.
Right. But it just goes to show, even with seemingly familiar topics, there's always more to discover. Thinking about different states of matter leads us to this question of, well, how do we classify and understand all the different substances around us, ready to tackle mixtures versus pure substances?
Bring it on. I'm feeling ready to dive deeper into the world of chemistry.
Perfect. Now, to understand the difference, let's start with thinking about, mixing ingredients together. Sometimes you combine things and they blend together, but they keep their own individual properties.
Right.
Like making a salad, for instance.
Okay, that sounds like a mixture because you can still, separate the ingredients back out.
Exactly. Each component in a mixture, it retains its own identity. But when you bake a cake, you're combining ingredients, they react, they change, and you create something entirely new.
So that's more like a pure substance. The components have chemically combined, right? You can't easily separate them back out.
Precisely. Water is a classic example of a pure substance. It's always composed of two hydrogen atoms bonded to one oxygen atom, no matter where the water comes from.
Okay, that makes sense. So a pure substance has a fixed composition, while a mixture's composition can vary, right?
Absolutely. Think about salt water. You can add more salt, you can add more water. It's still salt water, just with different concentrations. There's no fixed ratio of ingredients.
Okay, so understanding this difference is crucial because it tells us something fundamental about the substance, right?
Yeah. It affects everything from its properties to how you can interact with it. And speaking of interacting with substances, there's one really crucial aspect of chemistry that we can't overlook: accurate measurement.
Ah, yes, measurements. They're the foundation of any scientific experiment.
Exactly. And in chemistry, we rely on the International System of Units, or SI units, to ensure consistency and accuracy, around the globe.
Oh, yeah, I remember learning about those. Meters for length, grams for mass, liters for volume, right?
Exactly. And here in India, the National Physical Laboratory, or NPL, plays a vital role in maintaining those standards, making sure our measurements are spot on.
So they're like the guardians of accuracy, making sure everything is calibrated correctly.
That's it. And that level of precision is super important when you're dealing with the incredibly tiny particles that make up matter.
Right, because we're not just measuring teaspoons and cups here. We're talking about atoms and molecules. And I gotta say, trying to wrap my head around the sheer number of those particles, even in a small amount of a substance, it can be a little mind-boggling.
Yeah, I get it. That's where the mole concept comes in to save the day.
Okay, the mole. I remember learning about it in school, but it always seemed kind of abstract, I'll be honest.
Well, think about it like this. You wouldn't buy 12 eggs individually, right? You'd buy a dozen.
Right.
The mole's kind of like that. It's a convenient way to group a massive number of things together.
So instead of dealing with trillions upon trillions of atoms, we can talk about moles of atoms.
Exactly. One mole represents approximately 6.022 times 10 to the power of 23 entities. It could be atoms, it could be molecules, anything really. It makes things much more manageable.
So it was kind of like a shortcut for dealing with those insanely large numbers.
Okay, I'm starting to see why it's so important. But how does this connect to the concept of molar mass?
Great question. So molar mass is just the mass of 1 mole of a substance. It's numerically equal to the atomic mass, molecular mass, or formula mass, just expressed in grams per mole.
Okay, so if the molar mass of water is 18.02 grams per mole, that means that 18.02 grams of water contains 1 mole, which is that huge number of water molecules.
You got it. It's this fundamental concept that allows us to convert between mass and the number of particles, crucial in chemical calculations.
Okay, I'm feeling a bit more confident about moles now, but
Hmm.
how does this all relate to chemical formulas? Well, chemical formulas are like a shorthand way of representing the composition of a substance. They tell us what elements are present and in what ratio. There are different types of formulas, like, empirical and molecular formulas, which give us different levels of information.
Ah, yes. I remember those terms, but it's been a while. Could you, like, refresh my memory on the
Of
difference?
course, the empirical formula tells you the simplest whole number ratio of atoms in a compound. It's like the bare bones recipe. The molecular formula, on the other hand, gives you the actual number of atoms of each element in a molecule, the full, detailed recipe.
Got it. So, like, the empirical formula for glucose is CH2O, but its molecular formula is C6H12O6. That tells us exactly how many of each type of atom are in a glucose molecule.
Exactly. And understanding both types of formulas is crucial when we're analyzing and working with different substances.
This is so fascinating. I never realized how much information is packed into a simple chemical formula.
It's like a code that unlocks the secrets of a substance's composition and behavior.
Hmm.
But to really understand how substances interact and transform, we got to move beyond those static formulas and into the realm of chemical reactions.
Okay, I'm ready for the next challenge. What should we dive into next?
Let's explore stoichiometry. Might sound intimidating, but it's really just the art of balancing chemical equations.
Ooh, balancing equations. That brings me back to high school chemistry.
It's a fundamental skill in chemistry. Just like a recipe tells you how much of each ingredient you need to make a dish, a balanced chemical equation tells you the exact proportions of reactants and products involved in a reaction.
So if we're looking at a chemical equation, what exactly are we trying to balance?
We're making sure that the number of atoms of each element on the reactant side of the equation is equal to the number of atoms of that element on the product side. All about conserving matter.
Okay, can you give me an example?
Sure. Let's look at the combustion of methane. That's the main component of natural gas. The balanced equation is CH4 plus 2O2 yields CO2 plus 2H2O. This equation tells us that one molecule of methane reacts with two molecules of oxygen gas to produce one molecule of carbon dioxide and two molecules of water.
Okay, so I see how the number of atoms of each element is the same on both sides of the equation. But what do those numbers in front of the molecules mean?
Ah, those are the stoichiometric coefficients. Super important. They tell us the mole ratio of reactants and products involved in the reaction.
So in this example, 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water.
Exactly. Knowing these ratios is essential for, like, calculating how much of the reactants you need or how much product can be formed in a given reaction.
Okay, I'm starting to see how stoichiometry is like the math of chemistry. It's all about the quantities involved. But what happens when you don't have enough of one of the reactants?
Ah, that's a great question. That leads us to the concept of limiting reagents. Imagine you're building a bicycle, right? You have plenty of wheels and handlebars, but you only have a limited number of frames.
Okay, yeah.
The number of frames you have would determine how many complete bicycles you can build, even if you have extra wheels and handlebars.
Right, because you need all the parts to make a complete bike.
Exactly. In a chemical reaction, the limiting reagent is the reactant that gets completely consumed first, stops the reaction in its tracks. It dictates the maximum amount of product you can get.
So it's like the ingredient that runs out first and puts a halt to the whole party.
Uh-huh, exactly. And it highlights why understanding limiting reagents is so important.
This is all making so much more sense now. I'm starting to see, like, how all these concepts are interconnected.
That's what's so cool about chemistry. Everything is connected. But before we jump to the next part of our deep dive, I have a question for you. We've seen how those ancient Indian chemists were masters of practical applications. It makes me wonder, what traditional knowledge are we overlooking today? That might hold the key to solving some of our modern problems.
Ooh, that's a thought-provoking question.
Hmm.
Makes you wonder what gems of knowledge might be hidden in plain sight, right?
It's a reminder that the pursuit of knowledge is, an ongoing thing. There's always more to explore.
Absolutely. Although we might have to save that conversation for another time, I'm eager to keep exploring the world of chemistry.
Well then, let's dive into the next part of our deep dive. We've laid a pretty solid foundation. Now we're ready to tackle even more fascinating concepts. Welcome back to the deep dive.
Yeah.
Ready to keep exploring the world of chemistry.
Oh, absolutely. Before we move on, though, something you said before really stuck with me. The fact that ancient Indian chemists were already thinking about atoms way before Dalton. That's pretty mind-blowing.
It really challenges, our assumptions about the history of science, right?
Totally. And it just makes you wonder what other groundbreaking ideas might be, like hidden in ancient texts or
Yeah.
traditions, just waiting to be rediscovered. Okay, sorry, getting a little sidetracked. Where were we?
We are about to dive into the fascinating world of solutions. They're literally everywhere, from the air we breathe to the oceans, even our own bodies.
Right, solutions. They're just mixtures where one substance dissolves evenly into another,
Oh,
right? But in chemistry, I guess we need a way to describe like exactly
yeah.
how much of each substance is present.
You're thinking about concentration,
Mm.
and you're right, that's key. There are actually several ways to express concentration, each with its own, strengths, depending on what we're analyzing.
Okay, let's break it down. I vaguely remember terms like molarity and molality from school, but it's all a bit fuzzy, honestly.
Don't worry, we'll clear it all up. Let's start with mass percent. That one's pretty straightforward. It's just the mass of the solute, that's the substance being dissolved, divided by the total mass of the solution, and then you multiply that by 100 to get a percentage.
So, like, if I dissolve 10 grams of salt in 90 grams of water, the mass percent of the salt would be 10%.
Exactly. You got it. It's a super simple way to express how much of a substance is present, especially in, everyday situations. But in chemistry, we often need to be a lot more precise.
Okay, so that's where molarity and molality come in.
Right. Molarity, denoted by a capital M, is probably the most common unit of concentration you'll encounter, especially in a lab setting. It tells you the number of moles of solute per liter of solution.
Okay, so if I have a 1 molar solution of sodium chloride, that means I have 1 mole of NaCl dissolved in 1 liter of water.
Exactly. And remember, a mole is just that giant number we talked about earlier, 6.022 times 10 to the power of 23 entities.
Right. Okay, it's starting to come back to me. So molarity is all about the number of particles of a substance in a given volume. What about molality?
Molality, with a lowercase m, is similar, but it's based on mass, not volume. It's defined as the number of moles of solute per kilogram of solvent.
So it's the amount of solute in a specific mass of the solvent. Why do we need both molarity and molality?
Good question. The key difference is that molality doesn't change with temperature, while molarity does. That's because the volume of a liquid can change as it heats up or cools down.
Oh, that's a subtle but important distinction. So if I need a measurement that's like super precise and won't fluctuate with temperature changes, molality is the way to go.
Exactly. Each unit has its own use, depending on the context.
Okay, this is making those hazy memories from chemistry class a lot clearer. I'm starting to appreciate the nuances. Is there anything else about solutions we should touch on before we move on?
One more key concept.
Hmm.
Solubility. It's essentially how well a substance dissolves in a particular solvent. Think about trying to mix oil and water. They just don't want to combine.
Right, like attracts, like, right, I remember that. Oil and water have different polarities, so they don't mix well.
Exactly. Polar substances tend to dissolve in polar solvents, like water, and nonpolar substances dissolve better in nonpolar solvents, like oil.
Okay, so solubility plays a key role in determining what kind of solution you can even create in the first place. Like chemistry has its own set of rules for matchmaking.
Uh-huh. You could say that. And understanding these rules helps us predict how substances will behave when they're mixed together,
Which is, essential for everything from designing new materials to developing medicines.
This is making me realize just how much chemistry is involved in everyday life.
It really is.
Now, thinking back to those ancient Indian chemists we talked about earlier,
Yeah.
it makes me appreciate even more how they were able to make such significant discoveries without all the tools and knowledge we have today.
It's pretty incredible, isn't it?
It is. Imagine trying to, figure out the composition of a substance without the periodic table or modern analytical techniques.
I can't even imagine. They must have been like incredibly observant and meticulous in their experiments.
Oh, absolutely. Speaking of the periodic table, that's a pretty significant tool in modern chemistry, right?
Yeah.
It organizes all the elements based on their properties and helps us predict how they'll react with each other.
It's like a chemist's cheat sheet. Totally. But how did we even get to the point of having a periodic table? There must have been some key breakthroughs along the way.
You're right. One of the foundational concepts that led to the development of the periodic table was this idea that elements combine in these specific, predictable ways to form compounds. We often call this the laws of chemical combination.
Okay, so these laws laid the groundwork for understanding how elements interact with each other. Where do we start?
Let's begin with the law of conservation of mass. It essentially states that matter can neither be created nor destroyed in a chemical reaction. It might seem obvious now, but it wasn't always so clear.
Right, so basically, if you start with a certain amount of reactants, you'll end up with same total massive products, even if they're like rearranged into different substances. No matter is lost or gained.
Exactly. Antoine Lavoisier, a French chemist, is credited with really establishing this law back in the late 1700s. He was super meticulous in his measurements and showed that even though substances might change form, the total mass always remained constant.
Okay, that makes sense. It's like those magic tricks where something seems to disappear, but it's really just been transformed into something else. What other laws helped shape our understanding of chemical combinations?
Another important one is the law of definite proportions, sometimes called the law of constant composition. This law states that a given compound always contains the same elements in the same proportion by mass.
So no matter where you find water on Earth, it's always going to be H2O with 2 hydrogen atoms for every 1 oxygen atom.
You got it. And that consistent ratio is true for every pure compound. It means that a compound has a fixed and unchanging chemical formula, which is, essential for identifying and characterizing substances.
Okay, I'm starting to see how these laws really helped pave the way for organizing and categorizing all the elements. But there's one more law, right? The law of multiple proportions.
You have a good memory. The law of multiple proportions is a bit more complex, but it's really cool. It applies when two elements can combine to form more than one compound. Think about carbon and oxygen. They can form both carbon monoxide, CO, and carbon dioxide, CO2.
Right, so the same 2 elements can combine in different ratios to create different compounds.
Exactly. And this law states that when that happens, the masses of one element that combine with a fixed mass of the other element are in a ratio of small whole numbers. It basically highlights this idea that chemical combinations happen in these discrete, predictable steps.
So it's not just random, there's an underlying order to how elements combine. That's amazing.
It is. And all of these laws taken together really provided this framework for understanding the fundamental nature of elements and compounds. They were crucial stepping stones toward the development of the periodic table and our, modern understanding of chemistry.
Okay, so we've got a grasp of the laws that govern how elements combine, but what about the forces that actually hold atoms together within a molecule? What are the secrets of chemical bonding?
That's a great question. It's a journey into the subatomic realm where we explore the interactions between electrons.
Ooh, this is getting exciting. I'm ready to dive deeper into the world of chemical bonding. Let's unravel those secrets. Welcome back to the deep dive. We're about to tackle one of the most fundamental concepts in chemistry, the forces that hold atoms together to form molecules.
It's a journey into the subatomic world where we explore the intricate dance of electrons.
Okay, so I remember learning that electrons are those negatively charged particles that orbit the atom's nucleus. But how do those tiny particles actually create bonds between atoms? I mean, it's not like they have little arms that reach out and grab each other.
No, not quite. It all comes down to electrostatic forces.
Yeah.
The attraction and repulsion between charged particles.
Okay, that makes sense. Opposites attract, so the negatively charged electrons are drawn to the positively charged protons in the nucleus. But how does that lead to bonds between different atoms?
Well, think of it like this. Atoms are always striving for stability, right? They want to have a full outer shell of electrons, which gives them a lower energy state.
So it's kind of like atoms want to complete their electron collection?
Yeah, that's a good way to visualize it. And to achieve that full outer shell, atoms can either share electrons with each other or transfer electrons completely. Those two strategies give rise to the main types of chemical bonds: covalent bonds and ionic bonds.
Okay, I remember those terms. Covalent bonds are about sharing, and ionic bonds are about giving and taking. Let's start with covalent bonds. How does sharing electrons create a bond?
When two atoms share electrons, they create this region of high electron density between them, a sort of electron cloud. And this negatively charged cloud attracts the positively charged nuclei of both atoms, pulling them together and forming the bond.
So it's like the shared electrons are acting as a kind of glue, holding the two atoms together.
Exactly. Water is a classic example of a molecule formed through covalent bonding. The oxygen atom shares electrons with 2 hydrogen atoms, creating those strong bonds that give water its unique properties.
Okay, that makes sense. What about ionic bonds then? How does the transfer of electrons create a bond?
In an ionic bond, one atom completely gives up 1 or more electrons to another atom. This creates ions, atoms that carry a net electrical charge. The atom that loses electrons becomes a positively charged ion, a cation, and the atom that gains electrons becomes a negatively charged ion. That's an anion.
So it's like one atom's becoming more positive and the other is becoming more negative, and then those opposite charges attract each other.
You got it. Think about sodium chloride table salt. Sodium readily loses an electron to become a positively charged sodium ion, Na plus O, and chlorine readily gains an electron to become a negatively charged chloride ion, Cl.
So those Na plus and Cl ions are then drawn together by electrostatic attraction, forming that, like, iconic crystal structure that we know as salt.
Precisely. And that's the essence of an ionic bond, the electrostatic attraction between oppositely charged ions.
Okay, I think I'm starting to get a handle on these different types of bonds. Covalent bonds, they're about sharing electrons, creating that electron cloud that pulls the atoms together. And ionic bonds are about transferring electrons, creating those oppositely charged ions that attract each other. But there's one more type of bond we mentioned. Metallic bonds. What makes those unique?
Metallic bonds are the glue that holds metal atoms together in a solid structure. Imagine like a sea of electrons freely moving throughout the entire metal lattice.
Wait, so the electrons aren't like localized to specific atoms in a metallic bond, they're just kind of roaming around?
Exactly. The metal atoms donate their valence electrons, the ones in their outermost shell, to this communal pool of electrons.
So it's like a giant electron sharing party.
Haha, I like that. And it's this delocalized sea of electrons that gives metals many of their unique properties, like their ability to conduct electricity and heat so efficiently.
Okay, that's starting to make sense. So the metal ions are held together by their attraction to this shared pool of electrons?
Precisely. It's a strong bond. It gives metals their strength, their malleability, and that, characteristic metallic luster.
Wow, it's amazing to think that these tiny particles, electrons, are responsible for creating such a diversity of structures and properties.
It is, and it all stems from the way those electrons interact and arrange themselves around the atoms.
This has been such a mind-blowing journey into the world of chemistry. We've gone from, like, the ancient roots of the discipline to exploring the subatomic forces that shape the matter all around us. I feel like I'm seeing the world in a whole new light now.
That's the beauty of chemistry. It unlocks this deeper understanding of the universe and reveals the interconnectedness of everything around us.
So true.